Welcome to this video. My name is Mark Scythian. The date today is May 25th, 2025. And this lecture is going to focus on sheet metal layout pertinent to a 90-degree bend to make a U bracket. So we have a sheet metal section of unknown length, but we do know its thickness and it has a standardized width. So there's a certain U bracket you are bending for, let's say, an APU mount with respect to aircraft sheet metal structures. And so you must calculate the length of the sheet metal section, the linear measurement. And so the finished product is a U bracket. So you go to the structural repair manual and you replace the bracket by, let's say, fabricating it because it's not in stock. And so you go to the shop drawing, and the mold length line, or the finished length, on the upper right side is 3 inches, the right side vertical, and then the mold length line 1 on the left side, the left altitude is 2.2 inches, and then the base mold length line width finished length is 6.8 inches. So that's what you have to convert the sheet metal section into. So this has to be bent with a sheet metal brake without inducing any stress risers, right? So the easiest way to accomplish the correct sheet metal layout calculations is to first take the curve. Of course, we're working with a 90-degree bend, but take the curve with respect to a circle and place the crosshairs through it. So this, or these, will function as the bend tangent lines, one for the vertical y-axis and one for the horizontal x-axis. So you'll notice that you're able to separate where the straightaway, the flat, ends, and then the bend allowance, the curved circumferential distance here, begins, and then it goes back to another flat. So we'll call this one flat 3, bend allowance 2, then flat 2, then bend allowance 1, and then flat 1. So if we add up all of these sections, we will know the unbent length. So that's the anatomy of the bend. So we can isolate very easily the flat from the bend allowance using the bend tangent lines, and then we have one more component called a setback right here, the SB. So we have one setback on the vertical axis, then we have another setback on the horizontal, and then a third one on the horizontal. So 2 on the horizontal, and then one last one on the vertical, SB4. So this blue section, this is the bend allowance, the BA. So this is a derivative of a circle, so it's a circumferential actual metal length of the bend. So it's a partial circumference. So that is added to the flat 3, and then to the flat 2, and then of course the flat 1 and the other bend allowance. So we can fill in that one as well. So now we've isolated the flats and the bend allowances, and then the only thing we have left to isolate are the setbacks. So of course that's the visual depiction, but then we have to actually calculate this. So we'll get to the formulas in a second here. And note, this particular lecture is only bending for 90-degree bends. In another lecture, I will show how to bend non-90-degree bends, like perhaps different bends outside of 90, either greater than 90 or less than 90. So this lecture is only going to focus on the sheet metal layout for 90-degree bends. So we also have something called a K constant. This is the coefficient from the point of neutral axis of the bend. They just call it the K constant. So for 90-degree bends like this, it's just the K constant is equal to 1.0. So it's pretty simple, actually. So to get the actual bend allowance, sometimes it's actually specified. If so, then you can just add it to the flats. But just in case if it isn't, you can use this formula. You can just take half the metal thickness, the sheet metal thickness, then add it to the bend radius, and then multiply it times 2 pi, the number of radians to a circle, and then divide it into 4, which is then a quarter circle radians. So that's the approximation then made into an exact value. So that's called the bend allowance, the BA. That's just a fancy term for the circumferential partial distance of the bend. Like if we were to straighten this bend out, that's the actual length of it. So then we have something called the bend radius, and this is also very easy to calculate. We just take the number of degrees out of a 360-degree circle, and then we multiply it times the unit measurement. In this case, we're doing in increments of 1 inch. So how much of that 1 inch 90-degree bend radius is just always 0.25. And so if you're doing international millimeters, then that would be millimeters, but in the US FAA system, then it's 0.25 inches. So that's the bend radius. That's a constant because we don't have any other degree bends. We have all 90-degree bends. So that's the bend radius, 0.25 inches for a 90-degree bend. And then so we label the finished length 3 inches on the right altitude, mold length line 3, the horizontal width, including the setback and the curve, like if we put this ruler to the side, the width, the finished length, which you want is 6.8 for the base, and then the left side altitude is the mold length line 1, so that is the F1. Okay, so now we can calculate the setback, and this is just the metal thickness plus the bend radius as one calculation quantity, then times the K constant. So we know a K constant for 90-degree bends is 1.0, so it's pretty simple. You can just calculate it. 0.064 inches plus 0.25 times 1. So this becomes 0.314 inches. So we can write that in there for the setbacks. We have 4, 2 on the horizontal, and then 2 separate ones on the vertical. So now you're able to separate the, subtract the setbacks from the total mold length line to calculate the flats. So now it's really simple. You just take 2.2 minus 3.14. So F1 is 1.886 inches. And then we have 2 setbacks on the horizontal. So we have to take 2 times 0.314 and then subtract this from 6.8. And then we have F2 of 6.172 inches. And then the F3 is pretty simple, just 3 minus 0.134 inches. So we get 2.686 inches. And so now we can put together the segment assembly of adding. So we have 2 bend allowances and 3 flats. And so if we add, starting from a sequence F1 plus B1, F1 plus BA1 plus F2 plus BA2 plus F3, that will calculate the unbent sheet metal length. So then we just calculate the bend allowance, the last part. That's half the metal thickness here on the right side. So 0.5 times 0.064 inches, right? Then we add that to the bend radius, 0.25. We get 0.282 inches. Then we take it to the next step. We take the 0.282 inches, we multiply it times 2 pi, or 6.28 radians. And then we get 1.77. Then we divide this into 4 quarter circle. So we have a bend allowance of 0.4425 inches. So now we can complete the calculation. F1 plus B1, BA1 plus F2 plus BA2 plus F3. So we calculate 11.629 inches is the unbent length. So now if we were to put the sheet metal brake starting on the left side, we would measure 1.866 inches to account for F1, and then we would place the start of the bend here, place that to the 0-degree mark, and then we would make a 90-degree bend, a little bit more, 91, 92, because when it springs backwards, if it's exactly at 90, it will be like 88, so you go a little bit more, but start at 90, you might get 88, and then go 91, 92, like unbend it, and then you have a nice 90-degree bend. And so if we add the BA1 length, which is 0.4425, to the 1.886 inches, we will then have it reach the length partial circumference of 2.3285 inches. And that's where you would mark it, and that's where the bend would, the sheet metal brake would end, and then you did it correctly. You accounted for this correct, stable bend without putting a stress riser in it. So you need a bend allowance of 0.4425 inches. So start from the other side going left, and then you are able to induce this flat 3 to 0.686 inches and start at 0, and then you bend. So you have this side bent, you bent it, so you'd put it in the brake this way, and then you would bend it upward like this. And that would be the 90. So if you add 0.4425 to 2.686 inches, you'll get 3.1285 inches. And that bottoms out at the 90, other 90. So that's for 90-degree bends, and then that's the translational bend allowance. Blue, that's what the sheet metal brake is assigned to do. Everything else stays flat. And then when you're done, you round this to 11.63, and remember you have a 1/30 seconds, or 0.01. 1/30 seconds is 0.03125 inch tolerance on each side. So you have up to 2 times that. 2 times 1/30 seconds. You have up to a 1/16 inch tolerance on both ends for the length. So that's why you can just round this to 11.63 inches. And in aircraft structures, there's always a 0.03125 inch tolerance per side on any measurement. So that's 1/30 seconds inch plus or minus on both sides. So if we take the totality of both sides on a cut, it would be 1/16. So you can just round this, you can actually round this 11.6. That's what you would cut out, and you would make your cuts. So if you add up all of the side to side plus or minus 1/32 inch, it still comes in within tolerance. And so if we keep going here, we have a calculated value of 11.63 inches for the unbent length. And then when you place the unbent sheet metal in the sequence first left and then right, you'll have this finished product here, this bracket, without any stress risers ready to be installed and riveted. So we have our depth in here, and we place our rivets, and then you have a structural sound. You might have a offset to place a rounded edge or chamfer here, and that would be your APU mount. So in accordance to the structural repair manual, but the shop drawing, you'd have to manufacture from this unbent length. So that is the methodology to solve for 90-degree bend sheet metal layout and its calculations. So thanks for watching this video lecture, and have a great day.